And it's my great pleasure to present Jonathan Ma, Incorporation of Benchtop Spectroscopy into Undergraduate Laboratories. So over to you, Jonathan.
Oh, hey everyone. Thank you, Catherine, for the introduction, and welcome to my presentation on incorporating benchtop NMR spectroscopy into undergraduate laboratories. Once again, my name is Jonathan Ma, and I'm an application chemist and analysis. We're based in Calgary, Alberta, and we manufacture benchtop NMR instruments. Today, I'll be talking to you about a sample experiment we have recently explored, as well as how you are able to use the benchtop NMR spectrometer remotely in an undergraduate lab. We hope that this will showcase the capabilities of benchtop NMR as an undergraduate teaching tool and possibly provide you with the ideas that you can incorporate into your teaching curriculum. Before I get into the sample experiment, I would like to briefly touch upon some key ideas related to the concept of meaningful learning. The overall idea of meaningful learning refers to how students will retain the information they were given even after finishing the specific course they were taking. First of all, this requires the cohesion of the following three learning domains: cognitive, which is students understanding the material; affective, which is the enjoyment of the material; and lastly, psychomotor, which is the physical skills they develop from the material, such as lab techniques or hands-on use of the instruments. Overall, labs are the ideal environment for meaningful learning because the learning proceeds through guided inquiry and personalized instruction. That is, undergraduate labs typically contain around 15 to 20 students, as opposed to the many hundreds found in lecture halls. And as most of us know, asking questions in a laboratory section is multitudes less stressful than that in lecture halls. In terms of instruments used for characterization at an undergraduate level, we will often think of those shown in this slide. Students will often start with a melting point or boiling point apparatus, as these are not as expensive as the others shown. As they gain more experience, however, they'll begin to use more complex instruments such as gas chromatography, sometimes coupled with mass spectrometry, FTIR, UV-Vis, among many more. However, when we look at the most reported characterization techniques in literature, especially in inorganic and organic chemistry journals, we notice that NMR solutions or solids is without a doubt one of the most widely used methods available today. With that being said, many students still never get to use an NMR instrument directly in their undergraduate laboratories, meaning that they don't develop the skills inherent to this important technique until they're in graduate school or employed in an industrial position. Unfortunately, traditional high-field NMR spectrometers are very expensive to purchase and maintain. They require trained staff for maintenance, need a form of centralized booking system for use, and suffer from limited accessibility for undergraduates, as many academics routinely use these instruments for their own research. And sometimes institutions just can't afford them. Because of this, students will normally be given handouts in the lectures or labs of a generalized or ideal spectra of the compound they may or may not have synthesized. By giving students these ideal spectra, they're unable to witness how a spectrum will often look like in a real-life scenario, such as those encountered in graduate school or industrial environments. However, some benchtop NMR instruments have already made their way into undergraduate labs for teaching NMR spectroscopy, therefore exposing students to not only the NMR instrument, but also problems they may encounter when gathering spectra of the unrefined product they have synthesized. This will give students a head start into the NMR world, as they're to encounter solvent issues like which deuterated solvents to use, impurities, unreacted starting material, imperfect integrations, and many more. Historically, there have been two extremes in this area: high-field NMR instruments and low-field relaxometers. High-field systems offer the best resolution and sensitivity, allowing for the detection and identification of impurities, connectivity within molecules, among other things. Relaxometers are robust, easy to use, and found throughout various industries for measurements of T1 and T2 values. We'd like to think we're somewhere in the middle, where we offer a robust instrument that can show connectivity within molecules and assist with structural elucidation, all while occupying a very small footprint and at a fraction of the cost of a traditional high-field instrument. Let's move on to the sample experiment. The sample experiment I'll be focusing on is a Fischer esterification leading to the formation of methyl 4-amino-3-nitrobenzoate, and we will use benchtop NMR spectroscopy to compare the starting material and the product to showcase key differences. First off, what is a Fischer esterification? It's both a natural process as well as one used in many industries. The reaction is of a carboxylic acid reacting with an alcohol under acidic conditions to produce your ester and water. A popular example is the aging of wine. Do you ever find yourself wondering why wine tastes more eloquent the longer you let it sit? It's precisely due to the Fischer esterification. During the fermentation process of the fruits used, acetic acid is released, aka your carboxylic acid, and reacts with the ethanol content in the wine. This leads to the varying flavors and scents of the wine. However, since acetic acid is a weak acid, this process takes more time than the one I'll be describing. In addition to this, some industries that also employ the Fischer esterification include, but is not limited to, pharmaceuticals, paints, dyes, etc. This sample experiment I'll be presenting follows work published in 2020 by Schweiker and group. We prepared methyl 4-amino-3-nitrobenzoate by refluxing a mixture of nitrobenzoic acid and methanol under acidic conditions as shown in the reaction scene. After we let that run for 24 hours, we did a liquid-liquid extraction to separate any residual starting material and possible impurities from the product. During the consecutive washes, as shown in the picture, the bottom aqueous layer starts to become clear. After 3 washes, we concentrated the solution under a rotary evaporator and was left with a fluffy yellow solid. After obtaining the final product, we took spectra of both the starting material and the final product to compare, the starting material being the acid on the left and the final product being the ester on the right. The first difference I'd like to mention is the hydroxyl group of the carboxylic acid in the starting material at 12.74 ppm, which does not show up in the product. The second difference are the protons of the methyl ester appearing in the final product at 3.81 ppm, which isn't present in the starting material. These two outcomes indicate that the reaction has successfully converted the acid to the ester. Similarly, in the carbon spectrum, we see the new methyl group in the final product appear at 51.79 ppm, which is not present in the starting material. And just as a side note, with a decently concentrated sample, these carbon spectra can be acquired in as little as 12 minutes. In summary, I've shown you a simple Fischer esterification with the synthesis of methyl 4-amino-3-nitrobenzoate, as well as the proton and carbon spectra of both the starting materials and products, which can all be done within a 3-hour laboratory section. This is an excellent opportunity for students to gather experience with fundamental chemistry techniques such as liquid-liquid extractions, solubility, polarity, and most importantly, allow students to obtain hands-on experience with multinuclear NMR spectroscopy. Moving on, I'd like to discuss how the Benchtop NMR spectrometer can be used remotely for undergraduate labs with a simple unknown isomer determination experiment. Given the current circumstance, instructors are finding it difficult to incorporate laboratory techniques into the curriculum. However, with the Nanalysis Benchtop NMR spectrometer having a built-in PC, students can access the spectrometer through virtual network computing. This then gives instructors the flexibility in allowing students to acquire and process NMR spectra at home. Today, I'll highlight this procedure with an unknown isomer determination experiment, where we have 4 isomers unknown to the students with a chemical formula C4H8O2. With remote access to the Benchtop NMR spectrometer, students can be at home while the instructor is in the lab preparing the samples. The students will then have their own designated time slots to access and analyze said samples. By limiting lab presence to solely the instructor, current safety protocols can be followed, all while students gain semi-hands-on experience with an NMR spectrometer. During the student's scheduled time slot, they can access the spectrometer, collect their spectra, process it using the analysis software, and upload that as an image, much like the image in this slide, straight into their lab report. In summary, with online learning being either mandated or recommended, students can gain experience with an NMR spectrometer without being in the lab. And with the built-in PC, anything done on a PC can be done in the instrument as well. There are many options available for remote access, such as quantifying mixtures, assessing a reaction's completeness, observing possible byproducts or impurities, and many more. Thank you for joining me in today's discussion on the incorporation of benchtop NMR spectroscopy into undergraduate labs. Hope the session was informational, and I encourage you to reach out to us online or during the Q&A session if you have any questions or comments. Have an amazing day and enjoy the rest of the C3 conference.